Okay, now we're going to talk about reflection and refraction. Okay, so we're going to treat light as a particle, and we represent them as rays, so like arrows. Quite like, so here's a light being coming in, and it's going to be reflected off of a smooth surface. So the reason it's smooth is because if it's not smooth, then it won't reflect completely. It'll have some kind of reflection, but it will be what's called diffuse reflection, meaning that it doesn't come off at a specific angle, it gets spread out. So here's the light ray coming in and the light ray reflecting. So that's what the reflection is, like a mirror. And right now we're just looking at a flat surface. So it's smooth, flat surface, like a mirror, flat mirror. Now, we define the angle of reflection to be the angle between the ray of light and the perpendicular, a line perpendicular to the surface. So there's a 90-degree angle between the surface and that. Now you could think, why don't we define the angle relative to the surface instead of the perpendicular to the surface? And I'll explain that in a second. So we show this as being an angle, theta, in degrees. So we call that theta 1, and then the angle of reflection is going to be theta 2. So again, the angle between the ray and the vertical line, the line that's perpendicular to the surface. Now the law of reflection for a case where you have a smooth surface is that theta 1 is equal to theta 2. So there's a symmetry. You could also say this angle here is equal to that angle there. It's the same situation, but we're going to define the angle relative to the perpendicular. So that's the law of reflection. Now, the question is, before we can talk about refraction, is why did we talk about the line perpendicular? So let's take a circle, and we have a line coming in, and we have a light ray coming in. This is a shiny, smooth surface, but it's not flat. So the light ray comes in here. So the law of reflection would say the angle coming in equals the angle exiting. So it's easier to draw a perpendicular line to this curved surface than it is to draw a flat line. So that's the reason we do it. It's just convenience. So then you have the reflective ray goes like that, and I'm going to make it so that these two angles, theta 1 and theta 2, now they have names. This is the angle, so we'll say angle theta 1 is the angle of incidence, and theta 2 is the angle of reflection. So again, law of reflection says the angle of incidence equals the angle of reflection. Okay, now if you want to talk about refraction, what is refraction? Excuse me. So we have a surface, but it's not a reflective surface. It's a transparent surface like glass. So the mirror is glass with a kind of like a metal backing on the backside, so it has some reflective properties. So this is like a lens of some sort. So you have a light ray coming in, and again you define the angle, and we still would call this the angle of incidence, so let's call this theta 1. So again, it's the angle between the line perpendicular to the surface and the light ray. Now, depending upon the properties of the two materials, there's going to be two different materials here. So the one might be, this might be air, and this might be glass. This might be air, that might be water, that might be water, that might be air. It doesn't really matter in terms of drawing this. It does matter in terms of which way this thing bends, but So we have the, again, theta 1 is the angle of incidence. And we'll call this theta 2. It's the angle between the perpendicular line and the ray. I'll call this theta 2. Theta 2 is the angle of refraction. So it's just like before, except this is refracting. So reflection, it bounces off. Refraction, it goes through the surface and bends, depending upon the ratio of the properties of the two materials, which we'll talk about next. The reason it bends is because the speed of light changes when you go from one material to another. So we think of light being constant at 3 times 10 to the minus 10 times 10 to the 8th. But that is the speed of light in a vacuum. It doesn't matter what the temperature is. Really, temperature is irrelevant in a vacuum. But if you have, if you go into a more dense material, then the speed of light will go down. The speed of light in air is almost equal to the speed of light in a vacuum because there's not a whole lot in there. It's a lot of empty space, but water has a significantly lower speed. So what will happen is, if you look at this relationship between speed, wavelength, and frequency, when you go between two materials, the speed is going to go down, say from a vacuum to glass. Speed of light's going to go down. So what will happen here is that the frequency doesn't change. Frequency unchanged. So what has to happen is that the wavelength has to get shorter in the same, for the same transition. So it depends upon how much the speed of light decreases in a material. It depends on how much the wavelength changes, and the wavelength change will relate to how this thing bends.